talk is creating data fabric for IoT with a project called Apache Pulsar. How many of you have heard about Apache Pulsar? Oh, great. I didn't expect to, but it's nice to know. So I'm the co-founder and CEO of a company called Streamlio, which was founded last year with venture Series A from Lightspeed. And we work a lot with Apache Pulsar to provide an end-to-end messaging / storage / processing system. So I'll be talking about how you can create an entire data fabric for IoT using Pulsar. So now let us, since the time is short, I will be running through the slides pretty fast because I have around 30 slides to cover. So anyway, so we are in a connected world where data is coming at a large velocity and volume in a continuous fashion. To give an example of a few of them in the IoT space, so you have the healthcare wearables in the form of smartwatches, smart glasses, and you're trying to get the data related with the brainwave, heart rate, blood pressure, calories burned, and how you can monitor all these various data that is coming out of your body to proactively predict what is going to happen or what are the things that you need to take care of. Similarly, in the case of oil drilling, where you need to detect, you want to detect oil leaks or spills so that you can do a proactive maintenance in this context. Like the major metrics that people end up measuring all this pressure, temperature, airflow, velocity, and those kind of metrics. And in addition to that, cable providers, they wanted to provide some kind of a way by which measure what is the quality of service that our internet is delivering for various applications. How do you measure them? So they might have the cable boxes and everything, and they wanted to get the data collected from that box and send it over to their cloud to understand which area has an outage, which area has what kind of service that they are experiencing and all. Again, these are all instances of the broad segment of IoT in the sense. Now let's go into a little bit more abstract, what an IoT environment looks like. So IoT environment consists of myriad of devices, ranging from light device to all the way to the cloud. So I have given some approximate characteristics about what a light device versus smart device versus an edge node and a cloud. A light device is typically sensors. They do only one functionality. For example, the airflow sensor is just going to keep checking for the airflow and send those metrics. And simple to configure, and probably has a lightweight protocol to communicate that metric. Whereas a smart device is typically has some low-powered processor like ARM processor that are running inside, and they are in general serve multiple functionalities. And in a broad characteristics fashion, it expects some kind of a basic computation in a logic that you can push some things into it, and a notion of some kind of limited storage for storing data and sending data out. Lightweight and proprietary protocols to communicate from the devices. Then you have the notion of edge node, which kind of aggregates a lot of data coming from those devices. I mean, from either a light device or smart device. So it's typically multi-core based, a couple of sockets, probably around 8 cores. It has some sophisticated functionality in terms of running multiple applications. It can do complex computation logic and a decent amount of storage as well. And again, for a protocol to communicate to the cloud, it might be using lightweight protocols or even proprietary protocols. Of course, cloud has a lot of multiple machines and versatile functionality about what are the computational framework like machine learning libraries or even Lambda functions, everything you can do in the cloud. And of course, it does complex and generic computation logic and lots of storage. You can store the data forever, or you can store the data as long as you want to retain them as well. So this is a typical IoT environment scenarios. Now there are multiple ways how the IoT architecture gets deployed. So one is you directly connect the light devices to the cloud. So light devices have this simple endpoint where they are looking at some simple sensor data, and then they are doing some simple HTTP protocols to give that data to the cloud. If the data is lost, the application is fine with it. So this is one architecture. Another architecture is where you have smart devices connecting to the cloud, where the smart devices are like continuously collecting data. They are doing some kind of processing on the data and before they're sending it out. So take the example of in an hospital where a surgeon might be using monitoring for the heart rate. That machine is powerful enough. Not only it does heartbeat monitoring, it can generate some kind of alerts. And if everything is fine, it might not even send data. Only when some abnormality happens, then the data is sent out. So from that point of view, it's smart. So this is kind of smart devices to the cloud. Then you get into all kind of other architectures where you have light devices with the edge, where you have an edge aggregator, and this is especially useful in a context where the edge could be disconnected from the cloud for some amount of time. Take the example of a train, where you have an edge box and you have a lot of sensors in the train which is collecting data about the engine and how it's performing versus what's happening in each of the cars in the train and other things, right? So there will be an edge box which is sitting on the engine and trying to figure out how the train is operating, but the train might not be internet connected to the cloud. So which means the edge is the point where you take localized actions and remedy that action. Then after the cloud connectivity comes back, you send it this thing. Similarly, you have the smart devices with the edge as well. And of course, you can have another set of these things where you have hybrid set of devices. Some devices are light devices and some devices are smart devices, all sending data in some form or the other for crunching the data. And of course, then you have the multi-cloud. So now, as you can see, the problem gets complex. So not only you have to capture the data from those devices, you have to do some kind of data transformations, then data movement, then process some data logic in order to observe some patterns in the data, so like anomaly detection, outlier detection, or heavy hitters, or how frequently there's some things occurring. So you have to essentially have some kind of a data fabric that can capture data, then process data, move data to the cloud, then also what you call process in a machine learning related algorithms on a heavy aggregation of devices putting the data together. So essentially you need some kind of a IoT fabric that needs the data to be flowing around. So what are the requirements of that IoT data fabric? So one is you capture data across devices on the edge and normalize or transform the data. One of the challenge in data processing is 80 or 90% of the time goes in getting the data to the right format that you need. So that is one of the important requirements of a data fabric. And move data from the edge to the cloud and distribute for processing. And when the movement occurs, it's possible that you might have a disconnected operation where I cannot move the data because my connectivity is not working. Especially think about 4G connectivity and other connectivity where sometimes people, even though they might have all the 24-hour connectivity, they might not use the connectivity because of cost reasons. Then sometimes you have to take proactive decisions at the edge itself, or sometimes on the cloud, depending upon how critical the nature of the decision should be. And process data centrally and push it down to the edge. For example, I have collected a lot of data from edge devices or edge boxes. Now I'm merging the data across all those devices. Now we need a way to compute those models. Then once the models are built, then you push those models so that those devices become intelligent based on all the data that you have collected so far. So you need to have some kind of a process data centrally and push intelligence to the edge. Then quick reactions to insights to mitigate risk, especially at the edge. And also because some of the IoT data could be very personal data, so which means you have to have secure the data while not only while moving but also during processing time. And today, like the state of the art is getting all kind of different set of projects, different set of systems and everything in order to glue everything together. So ideally, a goal to achieve is a single system that can encompass the entire data fabric, so which is easy to manage and deploy as well. And so I've given some requirement in terms of what are the three broad pillars that you need in order to realize the data fabric. One is notion of messaging, a notion of a storage, and notion of data processing. So if from a messaging point of view, you need very fast ingestion of data, then you need no data loss, then you need some kind of security and encryption as the data is being ingested as well as moving around. Then it should support for millions of devices, like especially in the IoT context. You can have millions of devices or several hundreds and thousands of stores sending data from their point of presence. Then it should be highly available and resilient, and authorization to share data, how to share data across multiple people who are working with that data to infer some kind of insights, and the support for some kind of a schema to identify what structure of the data is in. And then you need to have storage. The storage could be at the device, or the storage could be at the edge box, or storage could be at the cloud. So able to write and read with low latency, and durability, which means once the data is given to storage, it cannot lose the data unless it's explicitly deleted. And it should be immediately available after writing the data. A lot of storage systems, the data is available only after a certain amount of time once the write finishes. Take the example of a Hadoop. If you have, unless the file is closed, the data is not visible for further processing, right? In our case, like it might be critical enough, the data piece. For example, if somebody's blood pressure shot up high, you might want to immediately get alert into that, right? So when you have such applications, when the data is returned, immediately you should be able to pick up that data. So of course, the data at rest should be at the encryption, and of course, you need authorization for storage as well. And the processing, there are a lot of processing that we've been used to, batch processing, real-time processing, and what type of processing that you need. Sometimes, most of the time, if you look at 80 to 90% of these things about data transformation, data routing, data formatting, then simple aggregations on top of it, and some thresholding. If this is aggregation exceeds certain this thing, then send an alert. And then the API should be simple so that a lot of people can use it. And support for multiple languages. Each one has a favorite language like Java, Python, and Go, then even WebSockets, Node.js. Then some kind of a state management so that processing can store the intermediate state and retrieve it whenever you need to. And of course, SQL support is something that everybody asks for, because everybody knows SQL because it's easy to write. So that is when we construct a data fabric using something called Apache Pulsar that has all the requirements that I talked about. And what is Pulsar? Pulsar is nothing but a flexible messaging plus streaming system backed by a log storage. If you are asking for one line what Pulsar is, this is what it is. And what does it do in this kind of IoT-like environment? There are three variations of Pulsar. Pulsar has been made to run on the cloud on a massive cluster size, and Pulsar can run on a single node with like 8 to 7 cores kind of this thing. And it also can run on a Raspberry Pi. So that way, using Pulsar all over at various points in the IoT, you can move data and you process data as well as store data and distribute the data to other applications that you like. So since I don't have a lot of time to go delve into the detail of a lot of the Pulsar aspects, I'll just give you an overview of what are the features that Pulsar has. Pulsar, it's completely durable in the sense like data is replicated as well as f-sync to disk so that you never lose the data at all. And it also provides multi-tenancy in the sense like if you have one single cluster, you can have multiple teams working on it. So which means, let us say like if take factory floors, there are one company might have multiple factory floors. Now each factory can see their own data, but they might not see across factories data for certain reasons or authorization purposes or whatever it is, right? So each factory you can map into multiple tenant so that the corporate can see the entire data across all the factories, but each factory could be one tenant, and each factory can run multiple applications in the context of namespaces, and you can have topics, which are the streams of data that is coming from several units of within the factory. Then it also supports tiered storage in the form of where if the data exceeds a certain size, Pulsar itself can handle all the data, but if you don't want to keep the data in a hot data store, instead if you wanted to data ages after a certain amount of time, you might want to store that in a cloud native storage like S3 or a Google Cloud Storage or whatever might be the case, right? So it supports tiered storage where data after a certain amount of time is automatically propagated into those tiered storage. It comes with data replication or across data centers out of the box. So you can have one Pulsar cluster on the edge box or one Pulsar cluster on the cloud, and you tell the Pulsar cluster at the edge box, hey, replicate the data to this thing. With one single configuration, it can start replicating the data or moving the data essentially, and which is ideal for an IoT kind of environment. And seamless cluster expansion, when you have a large set of data coming from several millions of devices, you can keep on adding nodes to the Pulsar cluster. It will expand without having to do any kind of heavy rebalancing, downtime, or whatever it is. You can continue to operate Pulsar, and you can do maintenance on Pulsar when it's in operation. Then we also have the notion of Pulsar Functions, which allows you to do flexible, lightweight computations in the form of functions itself, like a Lambda function. This function can run on the edge box, or it can be run on the device, or it can be run on the cloud as well, on all Pulsar instances. And it has a multimodal way of deploying. In the case of box itself or the device, it's deployed within the JVM itself. So that you don't need extra resources in order to run those computational logic. So Pulsar also supports a lot of unified message modeling, where you have the work queue model as well as pub/sub like model. It provides high throughput and latency, and it's highly scalable. If you have millions of devices, then you might want to make sure that all the data for each device is collected together. So you can do millions of devices. Pulsar runs around 2.3 million devices, million topics at Yahoo itself. So now, where does the Pulsar get all its strengths? Fundamentally, Pulsar is different from a lot of these traditional messaging systems, because it has what you call a decoupled architecture. So it has the notion of a broker followed by bookie. The broker is the one which is serving data. Bookie is the one that stores the data. So because of the fact these are all separated, you can increase the serving needs by scaling the broker, and you can increase the storage need by just increasing the scale of the storage itself. And in addition, Pulsar also stores the data in a notion of data segments. So in the sense, like each partition of the topic or whatever it is chopped into smaller segments, and the segments are stored in the underlying storage. Because of that, when some nodes die or whatever it is, the recovery time is pretty fast, because you do many-to-many recovery process, because multiple nodes are participating in the recovery. And whenever you wanted to query the data on a single partition, you don't hit only one disk. Because of the fact the segments are spread across multiple disks, you can read all the data of a partition in one single shot using multiple disks, so that you can exploit multiple disk bandwidth. So data movement. Pulsar can move data seamlessly from one data center to A to data center B, and this property is the one that we exploit in IoT kind of context, where an edge Pulsar box can send data to the Pulsar running on the cloud, where the cloud is aggregating a lot of edge boxes data coming from the from the factory floors or manufacturing floors, and getting aggregated there. So it can produce at multiple different data centers and consume at different data centers, or it can do a active deployment or active standby deployment. You can have all kind of, you can even do synchronous deployment or asynchronous deployment. So it's all integrated into the message flow as a single system. And also like a simple configurations to add and remove regions, or adding devices or removing devices. Then similarly, you can do asynchronous and synchronous replication as well. So, and I talked about multi-tenancy provides, where you have notion of a tenants and teams, and within a team you have the notion of applications. In this context, we have one product safety as a team, which in turn consists of ETL as one of the applications, and fraud detection is another application. And within that, you have the notion of topics. It has authentication to verify one team member does not get access to other team members' data. Then you have software isolations, where each team gets a quota. You cannot have more than certain amount of quota size. So then you can even isolate them in a hardware fashion as well. So each team can have some amount of storage quota as shown in this figure, like where marketing gets 10 terabytes, whereas product safety gets 7 terabytes. Now, Pulsar clients could be written on several languages, in addition to the WebSocket support. For example, in the case of light devices that I mentioned, they might just support HTTP protocol. So Pulsar supports a REST way of ingesting data, in addition to all the other languages like C, C++, Java, Python, and Go. So, I mean, Pulsar has been running in production for 4+ years on several companies, and this is the largest that we have pushed it so far. And this is just a handful of companies that have put in the slide, but around 100 plus companies have started using in some form or other. Now, how do you process data in Pulsar? So there are three aspects in which you can process the data in Pulsar. One is consume data as it's produced, so which is, I write my own consumer, I write my own processing. And then Pulsar provides something called a lightweight compute, which is to transform and react to data as it arrives. In the sense like as the data is continuously coming in, you can do some amount of processing, like in the form of data transformations, ETL, data conversion, even routing, then counting, aggregations, all kind of things like that. Then finally, since we store the data in the storage, Pulsar itself has a storage, you can query the interactive streams. If you store the stream of data for a particular device, how to slice and dice the data. Hey, can you do, like a week ago, did this threshold for this device that is monitoring the blood pressure exceed certain value? So you can query that old data as well too. So the lightweight compute is an abstract form of like a regular functions where you have incoming messages. Functions can take multiple inputs, and it can emit output messages based on the logic that you express in functions. How does the function looks like? It's very simple. You just derive from a Java function and write your logic, apply logic, and tell this is the input set of input topics that I need to grab data from, and this is a set of data that I have to write in the output topic. It just keeps going. So it supports all kind of processing guarantees, like at most once, at least once, effectively once. It's controlled by runtime by the user. When user gives the, when you submit the function, at the time you choose what semantics you want. And remember, this processing also can run on the edge, where when you submit the function, you have a REST endpoint by which you can remotely submit a function to execute on the device, or even in the edge node, because the edge nodes might be running on a remote location which you might not even reachable to, right? So if as long as the internet connectivity and other things, you can submit the computation logic to run on the edge as well. So then finally you have querying by using Pulsar SQL, where because of the fact already data is stored in the form of smaller segments, and that data will be read simultaneously by a SQL engine to answer the SQL queries that you posted. So now Pulsar Edge, I mean we can still have the separation of broker and bookie, and the function running on a single node. It requires like 100 to 200 MB of footprint, and runs like on 2 to 3 cores and 512 MB of memory. Function in separate JVM, or you can run it on the same JVM as the broker itself. On the Pulsar on the device, which has a 60 to 70 MB of footprint, runs in only one core, and 256 MB of memory is good enough. I mean, this is essentially like what we have done with the Raspberry Pi. And functions run as a thread in the broker, because you don't want to instantiate another JVM in order to run your computation logic. So everything runs in one single process by itself. Now tying everything with the Pulsar together, how Pulsar can satisfy the needs of a fabric that we talked about. As I said, like this is a hybrid environment where you have seen Pulsar running on a device, which is running a function here, like a filter function here, which is capturing the data from the device, and the data is replicated using the geo-replication capability of Pulsar into a Pulsar Edge. Meanwhile, lightweight devices can use a WebSocket in order to pump data continuously into Pulsar, and then you can do some kind of data transformations on the edge itself before even data is moved to the cloud as well too. So some kind of localized processing that you can do. For example, I wanted to get all the data coming from all the factory flows into a normalized form, right? So you can push the transformation function from your cloud into the Pulsar Edge so that every data is on the same common denominator, right? So, and similarly, some other Pulsar function can look at some kind of aggregation function that it's running so that it can look at whether some threshold is exceeded of beyond a certain range. If it is exceeded a certain range, immediately you can trigger some kind of alerts. So now once the data comes into the cloud, now the Apache Pulsar cloud version can distribute the data to for further additional processing like dashboards or even monitoring and BI, and do a data distribution in terms for other applications to consume, like historical repository like data lake, which is used for BI and other things extra. So that's all I had. Thanks for listening. You have any questions? Yes.
Is there a support for data versioning?
Data for streaming?
No, data versioning. Like for example, when I...
Oh, okay, data versioning. So you could version the data. It's not inbuilt into that, but there is a function that we have written, special built-in functions that allow you to do the data versioning.
So it's up to the app developer.
Yes.
So how do you migrate them when you have a lot of devices, like thousands of devices?
So you can associate a particular device with a particular topic, and the data for that topic will be specific to that device. So which means all the data coming from the device will be continuously collected, and if you change the particular data, then you can change the data itself. So which means it will be a complete log-like thing. It will be a complete log of all the data retained depending upon your retention period for the how long you want to retain the data. Now you can aggregate all the device data separately for some aggregate processing, where you can take the data from the device topic, transform it, and put them into all of them into one single this thing. Again, that is all in Pulsar, because Pulsar function will take input from a topic and put the data back into another topic, right? So then you can store the data back into Pulsar itself. So you don't need multiple external systems to all bring it together. You can do everything within Pulsar itself. Yes?
So how is it different from an already existing Pulsar system like Kafka?
So, I mean, I didn't have time to go through all the details, but remember all the list that I gave up I gave in the first about what this Pulsar is. That is the major difference. If you want, like, let me, this is, I can go back to that slide. So this is the one slide which has all the properties. In addition to that, Pulsar can run on Raspberry Pi and also execute on the Raspberry Pi. So which is very small footprint. So especially geared for more on the edge kind of computations. So these are all the various differences from Kafka as well too. And Pulsar was designed from ground up from where it was designed for systems where like RabbitMQ, JMS queuing kind of systems, plus Kafka-like system, and they want to consolidate all of them into one single system. It was designed basically, that's where the unified messaging model comes into play, where you can do RabbitMQ style queuing, as well as pub sub like Kafka-like queuing systems in one single sort. And in fact, a lot of ideas from Pulsar has been gone on to influence other messaging systems as well, like offset management. Offset management, you don't have to manage any of the offset. It's already inbuilt into Pulsar completely. Whereas if you look at the history of Kafka and all, offset management got inspired after Pulsar was put into production at Yahoo. Then, and Pulsar also supports deduping, so that exactly once, at least once, and at most once, do not suffer in performance. They are in 10% of performance of each other. I mean, I can go on for a lot of time, but again, yeah, yes.
Does it support the replay?
Yes, you can go back in time and replay from data also, and we can retain like 6 months or a year worth of data as well, because ours is a separation of brokers and bookies, right? The bookies are the storage. We can keep on adding storage as long as you want. So essentially, we have proven Pulsar to retain more than a year worth of data. Retain this, yes. Yeah, you can have a it's all open source. Apache is open source. You can download it and try it out.
Yep.
So Pulsar uses Zookeeper only for metadata, and again, that is not exposed to the client at all in any way. So the point of interaction for Apache Pulsar is only the broker, which sits behind a load balancer. Or if it is in a smaller edge device, the Pulsar one single process makes a Zookeeper also part of the one single process itself. So that is why it's very easy to deploy in an edge node. Yes. Okay. Oh, thank you. If you have any questions, I'll be around.